Okay, I think we should start, and then people will come over when they woke up. So yesterday we discussed a bit of the geometry of asymptotically flat spacetime, and yesterday I tried to emphasize the features of scry of the boundary that can be derived from the definition, but also the feature that can be the Penrose peeling, which is completely, essentially coordinate-free statements. Today, I want to spend the whole hour discussing BMS coordinates, asymptotically flat spacetime from the point of view of BMS coordinates, and relates in this way to the first lecture on the geodesic congruence. So what we already, so let me pick again here some asymptotically flat spacetime. So G tilde mu nu is the physical / Einstein metric. G mu nu without tilde is the unphysical one. So as we, yeah, please, yeah, thank you, thank you. Boundary of M tilde boundary. So there is an unphysical spacetime N, which is essentially M tilde union with scry. So we saw that at least locally on scry, we can always choose coordinates which I'm going to call x little a equal u, z, well, depending, it's going to be u, y, a, and y, a would mean z, z bar, depending on the context. If I need to have some, so z, z bar in general are the coordinates, but if I need to write some expression with explicit sum, it's better to use this sort of notation. So we can always choose them such that, so at scry, at least in the local neighborhood, say, such that, well, the universal structure was the normal, and the dxa is just d du, and the induced metric h is just the round sphere metric. Yeah, so this I'm going to write h a b with s2 d y a d y. So you can always choose a coordinate and good representatives for omega such that this is true. This is what we discussed yesterday. So in this sense, this was for this reason that it's fair to say that this is why people call this structure universal. It's always the same in any spacetime. There is no local degrees of freedom. And then, so the idea BMS, essentially, then you can extend this coordinate system to get BMS coordinates. So these are coordinates on scry. Now we want coordinates on the spacetimes itself. So position, once we made a choice of these adapted coordinates u, z, z bar on scry, then there is a unique coordinate system u r equal omega minus 1 z, z bar in the neighborhood. Well, let's say, yeah. Let's say on M. Of course, it's only going to make sense neighborhood, but such that the metric, so I'm going to write the physical metric, so ds squared plus tilde, g tilde mu nu, dx mu equal. Yeah, so will I have enough? I need to write it here this way, I have more fun, so that ds tilde squared equal g mu. Equal 1 over omega squared, omega cube e2 beta du squared plus e2 beta 2 du d omega plus h ab dy a minus ua du dy b minus ub du. Yeah. Or let me write this in terms of r, because this sort of thing depends really on your taste, on people, whether you want to use this r, which is going to infinity, or omega going to 0, boundary defining function. So in terms of r, you would write e to the beta v divided by r, du squared minus e to beta 2 du dr plus r squared h ab dy a minus ua du dy b minus ub du. With, okay, so it's not enough, it's the first part, but with the following fall-off condition, r cube minus 3, r minus 3 v. So these v's, betas, h, they are function on scry. Well, no, they are function of every coordinate. And so v, for example, it should be as follows: as r goes to 0, equal little o of 1, or maybe big O of r. Maybe that would be more explicit, somewhat help. So this guy should go to 0 as r goes to 0. Same for beta. Well, yeah, this is just to emphasize that they are all function of every coordinate. And yeah, HAB equal, so it's not going to 0 because I want this, the boundary metric, to be the round sphere metric. So it's just depending on ZZ bar plus some term which is going to 0. And it's not, and so there are something else that we need to require. We are going to require that the derivative of the determinant of this big H, so the R derivative is 0. Okay, so this coordinate system is called BMS gauge. So this, I mean, there are a bit. So
in the last line of the upper blackboard, there is e to the beta or e to the 2 beta?
okay, yeah, it's probably 2 beta. There's probably a typo in. Yeah, no, it must be the same. So yeah, it's a typo. It's 2 beta. You're right. Yeah, it's really the same expression, so it should be the same. So of course, I mean, there would be different names you could give. In particular, this V is a bit, I mean, it's part of the definition. There is this omega cube in front of the V. Oh, I didn't put the V upstairs as well, right? Yeah, here there is a V, so E2 beta V du squared. V du squared. So it's part of the definition of this V that there is this term sitting here. So I mean, whether you like it or not, it's a matter of conventions, but I'm following paper. I'm following here, I think, Barnish and Troussard paper where they write, they run through the computation very explicitly. I like to use this paper as a reference, and I think this is following their conventions. So this feature, this in particular, so just about some terminology and notation. This is really what makes the gauge BMS gauge. Alternatively, I'm not going to use this anymore, but alternatively, you could use another choice. Alternatively, would have been not to choose to fix this, but instead choose beta equal 1. So we could take beta equal 1, and this would be Newman-Unti gauge. So it's just a bit of a terminology for when you're discussing with people, try to understand what they mean. So alternatively means really it's either this or this as a choice. Okay, it's a nice coordinate system. What BMS did, maybe, yeah, what BMS did, and I will give you the outcome of this soon, is that you take this expression, you write each of these functions in powers of R, you solve Einstein's equation order by order, and they realized that they could do this. So I would give you, remind you or tell you how this works soon. But at this level, for now, we did not impose Einstein's equation, so it's just a coordinate system which is coming from this choice of coordinates on the boundary and the fact that the boundary exists and it has the structure that we discussed yesterday. So at this stage, no Einstein equation at highest order are imposed. Okay, so the thing I'm going to do is prove tell you how we construct this coordinate system. It's not a big deal, but it's not something which is very, I mean, these sort of proofs are not very easy to find in the literature, even though it's not big, big deal. Because typically people either take this as a starting point for a definition of asymptotically flat spacetimes or Penrose definition, but you see they are equivalent. So it's clear that any metric like this is asymptotically flat in Penrose sense. But now I want just to run through the proof of this to see how we construct this coordinate system. Yeah, another remark that I should say before. So this coordinate system, U, R, Z, Z bar, really they are extending the coordinate system from the boundary. You choose the coordinate system on the boundary, and this is an extension. So if you take R equal infinity or omega equals 0 in this coordinate system, you should recover this one. And this is like the essence of the construction. So the first step is to start. Well, I mean, the idea is that, as I told you in the first lecture, this is essentially choosing a null geodesic congruence. So the idea of the proof is that we are going to construct this null geodesic congruence, and then this will be just the coordinate system associated with this. So how does this work? So first of all, we use the fact that we have this coordinate system on the boundary. So we have this adapted coordinate system U, Y, A on scry. And what it does is that it defines a frame. It defines, well, it's a degenerate frame, really. Degenerate frame at scry, which is, well, it's rather obvious. So you just take N, which is the normal restricted to scry, is du in our coordinate system. But now you can define M, you make some choice, And let's say I'm going to define it to be this guy. 1 plus d squared, 0 square root of 2, dz, and m bar is the complex conjugate, of course. Okay, so it's a degenerate null frame in the sense that this guy is contracted with the metric is 0, and these ones, they are when they contract, each of them are null, and when they contract, they give you 1. So okay, let me write it explicitly. So h n m h n n equal h n m, etc. M bar equals 0. The only non-zero, maybe the only non-zero contraction is the fact that h m bar equal 1. Now, this is a frame which is degenerate along scry. The idea is that we can extend it into a null frame at scry. And it's going to be unique. This can be uniquely completed into a null tetrade. Null tetrade is n. So n essentially is du, m is proportional to dz, and L, which is your complete, gives you essentially, you should think of L as being dr, but at this stage dr is still, we haven't defined the r coordinates, but at the end of the day, this is what it will be. So think so this is just a tetrade as straight, and think that L is d over dr. So what's the picture? So we have scry. Here we had the n, which is the normal inside of scry. Because we have this coordinate system, we have a foliation by u, which is defining for us this m. And as I explained in the first lecture, once you fix n, well, a null tetrade is unique to choosing m, but here m is chosen by z. So there is a unique L, which gives you the completion into a null tetrade here. Okay, so this is really the choice of coordinates on the boundary, which defines this outward pointing L, which is going to, so what we get is a transverse null vector to scry from the coordinate system that we chose on scry. Okay, that's really the key feature here. So this was the first point. First point was construct L, construct this transverse null vector, and it's unique due to the fact that we chose already coordinate system along scry. Now, second point is, so now by construction, let me explicitly write this, by construction, L mu is a null transverse vector to scry. And transverse really means that it's not along scry, it's pointing outward, it's pointing towards your spacetime. So now what we can do is we have a null vector, we have an initial hypersurface, we can flow along this null vector. How do you flow? Well, you solve the null geodesic equation. Null geodesic equation is a second order PDE, first order PDE, which is conformal invariance. That's going to be crucial, which we can solve. we now construct a null geodesic congruence, so a space of null lines. By solving the null geodesic equation, the null geodesic equation. I mean, it's a geodesic equation, really. For curves starting at scry with initial speed L mu. So the point is that this since scry is not well defined for the physical metric, this only really makes sense for the this really makes sense at for the unphysical metric G mu nu. But since this is an exercise, since null geodesics are conformal invariant, well, in fact, this defines null geodesics for scry, for the physical metric. This gives geodesics for G tilde mu nu as well. So like here, we're really using the fact that null geodesics, and this would not be the case if you were trying to do anything like this for time-like or space-like geodesics. Null geodesics, they are really conformal invariant, so I really do not care whether I'm using the physical or the unphysical metric. Good. So first point is we use the coordinate system on the boundary to construct this frame. This defines for us a transverse null vector. Then we solve the null geodesic equation, and it gives us a flow of, defines the null congruence geodesic in the bulk. And now that's essentially it. We construct the coordinate system by flowing the coordinate system, by keeping the coordinates constant along the null geodesic. So the third point. We now extend U and YA in M by requiring that they are constant along the null geodesics. And since we already have omega, because omega is part of the omega is part of the definition of an asymptotic flat spacetimes. So together with omega equal r minus 1, this defines u r equal omega minus 1 z bar. So really what the way it works is you choose a point in your space-time. Here, how does the coordinate system work? Well, you have omega, which is telling you how far from scry you are, and then you follow this null geodesic, you end up at scry, and you just look at what is the point, what is the coordinate value of the point along scry. Yep. Okay, so we constructed the coordinate system. Now we need to check that indeed the metric must be of this form with this proper coordinate system. So then we have the coordinates, so we just write down the metric. So we must have, I'm going to write the n-physical metric, g mu nu gx mu gx nu equal omega to the cube e to beta v du squared plus e to beta 2 du d omega plus hab dy a minus ua du dy b minus u b du. Okay, so why is this? Because it looks not like completely generic metric because of the following. So I will check this for you as an exercise. So 1 g omega omega equals 0 because, well, because by definition of the coordinate system, L equal d omega. This is what generates the congruence. Generates the congruence. I mean, yeah, maybe I should not write this because really, well, L equal d omega generates the congruence. So this must be null, and in particular, this object should be 0. Yeah, I'm going to miss some room. Let me write this there. Where is the good?
Why we have omega to the third power? If in the proposition we had in the first term of the metric 1 over r, and here we have omega to the third.
Right. But this is the physical metric, g tilde, and here I'm writing, so this is the, yeah. So, okay, first constraint on this metric, d omega omega has to be 0 just because by definition of the way we constructed the coordinate system, L is the null vector along the congruence. But then the congruence also should be null geodesic. You can check that this imposes that dr of ga omega equals 0. And this is an exercise to check that this is the same as dl L mu is proportional to L mu. Proportional because I don't want to choose the geodesic parametrization. And then yeah, and then third point, so this depends on R, but you could have a constant, and this would be, but this constant must be 0 because, yeah, let me write this like this, because at initial time, gz omega evaluated at scry, which is the same as g dz d omega evaluated at scry, is the same as m, well, it's proportional to m mu L nu g mu at scry, but this should be 0 by definition of the null tetrade. So this guy has to be 0 at scry, but then it's constant in time, so it cannot appear, it's not there. So yeah, this is the only terms. So this metric is, these are the two features. So this equals 0. Well, I mean, yeah. So altogether, this implies that gz omega equals 0. So this plus this gives you this generic form of the metric. And then the fall-off condition comes from the fact, from the conformal compactification. It comes from the fact that, by definition, g mu nu evaluated at scry is finite. Okay, this is the unphysical metric. Which by Penrose's definition must be a finite number, it cannot blow up. And therefore, the coefficient here, they just need to be, they have to be finite as you reach the boundary. So this immediately means just that u r ya equal O of r minus 1, ua equal O r minus 1, etc., etc. H A B equal H A. Okay, so good. We constructed the coordinate system. We found that the metric is constrained to have these two coefficients to be 0. The fall-off are fixed by Penrose conformal compactification requirement. Last step is to fix the is to obtain this data of H coordinate freedom. So what's the only freedom that we have left at this stage? Yeah. Yes, this is the geodesic equation. Okay, very good. So, so there is always this subtlety what we mean by a geodesic, whether we are thinking of the geodesic as being parametrized or unparametrized. Here, at this stage, we did not choose, and I don't want to choose, the fact that the omega is the geodesic time along the null geodesic. I didn't say anything about this at this stage. So the number here, whether this is 0 or just proportional to the vector, would fix the parametrization along the curve. So I don't want to fix the parametrization, so all you ask for is that the line itself, not the parametrization, is geodesic, so it's just proportional. So if you were, I can already say easier, if you really were insisting, oh, I want the affine parametrization, it looks like a very good choice, you impose that this is equal to 0, this would give you the Newman-Unti gauge, beta equal 1. Okay, this is one very good choice. You could make this choice. But BMS, they choose not to do that. So you have conflicting choice of gauge in the literature. So if you like this affine parametrization, for very good reason, because it's somewhat physical to like follow the null lines with the affine time, then you will choose Newman-Unti. This is this gauge I chose in the first lecture. But in the BMS literature, they felt for not even sure what reason, but they felt this was a good choice to make this other gauge, which I'm going to do now. But then you cannot require this. You cannot require this to be 0. It has to be proportional to m. So precisely, this is what I was about to discuss. Where is the freedom in time in this construction? Now, we can still use, so how did I construct the coordinate system? I choose u and z bar on the boundary, flow is my null geodesic, and then I use omega as my third coordinate, and my fourth coordinate. But omega is not unique, so we can still use the freedom, so the conformal freedom, really. Omega goes to lambda of x omega. To change, to take whatever time we want. So by time I mean r coordinate. So it's time of the flow coordinate. We want, and here you make a choice. So either you impose, as you were suggesting, the null geodesic equation, which would give you beta equal 1. This is Newman-Unti. Or you might want to make another choice. Again, this other choice is you impose that the determinant of H is 0, does not evolve in time. Well, this is what it is, and this is BMS. Okay, and we have at this stage, if you think about the way it's been constructed, we have fixed completely all possible freedom in the way of constructing the coordinates. Okay, so I think that's it. So from the perspective of from this perspective, the fall-off condition in the BMS free functions, they are really given by the conformal compactification. It's just a requirement that the physical metric should be finite at the boundary. That's all this is. Okay, so from this perspective, you could imagine take many follow-ups. I think back in the days, you could imagine take many crazy follow-ups in R's. You have no idea. You could choose one thing or another. But conformal compactification gives you one nice follow-up condition, just following from the fact that the physical metric should be finite. Yes?
So you said this form of the metric doesn't use the field equations?
At this stage, no. Yeah.
To what extent is that true? Because didn't yesterday we use the field equations to argue
Very good.
finite?
Right. So, okay, what I mean is it's a good point. So it doesn't use field equation at, yesterday, remember, what I really used was just the fact that shortened tensor has to be finite. So that's, yeah, indeed, this is what you need to use.
So it's that we haven't said what the stress tensor is on the right-hand side, essentially?
Yeah, that's what I mean. Yeah, it could be whatever it wants at this stage. And yeah.
Can I ask a follow-up question?
Please, please, please.
If we have, let's say, a higher derivative corrections to gravity or something, we can always shuffle those terms into what we call the stress tensor, but will those be guaranteed to have the same fall-offs, or can higher corrections, like from EFT or something, dismantle this? Do you know?
Generically, I would expect that it. I think you're asking if I have higher derivative gravity theory, can I always take asymptotically simple spacetime as a good class of spacetime?
Right.
Naively, I would say that you could create a situation where it would be very bad, I would imagine. But also, I would imagine that in many situations, it would be many deformation of GR would just be same boundary condition. It's just that the way you solve the field equation order by order are different. I think most of the time that would what you mean, but you could imagine. Okay. Yeah, I don't know if anyone tried to do this computation. Yeah.
Sorry, I have the question. How do we read the follow-up condition into that?
Okay. So yeah, okay. So for example, you want this first coefficient here just to be finite. So I mean. Okay, so maybe you're right, maybe.
It also seems possible, it seems like you set it to 1, right? So it's strange that you say that it falls off.
Okay, let's do the exercise slowly. Yeah.
When theta goes to 0, then exponent goes to 1,
Yeah.
and then we have proper normalization of vectors.
Right.
We have 2 dv d omega, which is 2 du d omega, which is 1.
Yeah, absolutely. This is the answer. So at scry, so these follow-ups have to do with what's going on at scry. So at scry, du d omega, as your colleague pointed out, would be this n contracted with L. So this is the nullity trade. Should be -1. Well, so okay, there must be, okay, there is a sign difference, which right, I don't know which convention I took here. But okay, plus or -1. So this coefficient should be just some number fixed.
Right, but I mean, it looks like, you can set it to, it can be a constant plus all the R minus 1.
Yeah, this constant, you see, this constant is really like changing the normalization of what you want to call your initial. So d omega is your initial vector field at scry. So changing this constant is really like changing the normalization you care about for L. So I explained the starting point of the construction is you start with this M, and then you want to construct L. And the way you fix L is by requiring the null normal condition. Part of the condition is n dot L equal 1. Maybe you want to, you could take equal 10 or 17, whatever. It's the choice of like, yeah. And you could take another number. It would be like another initial L vector.
As long as beta doesn't go with R, so it doesn't actually
Right.
go to
Yeah. It's there are different choices which are more or less natural depending. Yeah, absolutely. Yeah. Also, okay, yeah. This is the same for this guy, right? The reason this guy goes to 0 is that you want the metric at scry not to have this dy du cross term. You really want the metric at scry to be just dz bar, just the round metric. So it all has to do. Okay, maybe this is finiteness together with the choice that we've already made at scry. We know we've chosen this u and z bar so that I erased it, but so that the normal n is just du, so that the metric is just 0 plus dz bar times the round metric. And this is all this requirement that fixes this to be 0 and this to be the round metric. Okay? So really, is what's happening is that you're making some choice at scry, and these are, there are many different choices you could make. You just take some that you like, and then you use the null geodesic flow to fix all the other, what's going on in the inside. Yeah, also let me comment on that question that indeed we use the field equation at leading order. I got asked this question yesterday. What would happen if you choose a different cosmological constant? If you would choose different cosmological constant, you would not get a null normal at scry. You would get an actual normal at time-like or space-like depending on lambda. So okay, yes, we are really using, this is really using the leading order Einstein's equation, but really the leading order. Okay, so this is how we construct the BMS coordinates. Yeah, please.
Question like the Newton scalars when you define them in terms of contraction to the Weyl scalar of potentials.
Right.
It seems like depending on the choice of setters that we make, we will get different coefficients even with the expansion.
Okay, so yeah, maybe just the way I presented it was not very clear. There are choices you can make in the tetrade. Well, which choice do you have in mind?
I mean, just if you choose another m.
Very good. Okay, so there are certain things. So first of all, if you're thinking of the Newman-Penrose coefficient, it's natural. I mean, implicitly what people mean is that they use the physical metric, because you could use the unphysical metric and you would just rescaling these different weight scales in R. So what people mean when they look at the fall-off of the Newman-Penrose coefficient is use a null tetrade for the physical metric. It just gives you this nice fall-off. Then there is a freedom in choosing the null normal tetrade, which I should say is also the freedom that we've seen many, many times. I'm sure many of you have realized this in this polarization vector that we discussed, that were discussed in other lectures. And then, so one of the coefficients is essentially invariant, and the others are not. The other would if you change the null tetrade, the other coefficients are going to transform with each other. Was this your question, or is that?
Yeah, no, exactly. Because
Let me write the example. So psi4, yeah, well, maybe you can please. Psi4 is while n m m n. Jerzy told me that I should use m bar really to fit with the canonical literature. So this is unique because if you add a little bit of n, m is not unique, but if you have a little bit of m, then this contracts and it's 0. Okay, so maybe you might want to add some sort of phase, and okay, there would be some phase for the psi4. That's all you can have. But psi3, which is while n, I'm going to make a mistake, of course, m bar n, I think this, L, is not so unique because if you L, you could add a little bit of n, which you would not see, but there will be a little bit of m showing up, which will give you a term like this. So psi3, in a sense, you see that if you change the null tetrade, you'll add a little bit of psi4 added to psi3. But if this guy is 0, then this guy becomes unique, and in turn, etc., etc. Right?
because in the expansion, I mean, there are some people who
Yeah.
not trained, but they say that some expansion coefficients correspond to physical quantities, right?
Sure.
The shear or the mass, or
Yeah.
and then you naively expect them to be invariant under certain settings. Right? But I
Very
guess
good.
it's
Okay. Okay. So this is an invariance because this encodes presence of gravitational radiation. So whether it's 0 or not is whether or not you have gravitational radiation. Yeah. Then psi3 is also some radiation type of behavior. Then psi2 and psi1 are real part of psi2 is like the mass, and psi1 is angular momentum. So first of all, one thing you should see is that if you have gravitational radiation, then the mass is not preserved, as I will recall. And so you should not expect that the mass is invariant, because precisely there is a flux term which is going to flux the mass. So if you change for example, if you act with supertranslation, it's like moving in time. Well, of course, the mass changing by some sort of radiation because it's sourced by the radiation. So that's fine. If you do not have radiation, then the mass is conserved, so somewhat Psi2 is okay. But angular momentum will mix with the mass, and this is just this usual fact that you can always, if you act with a translation, you're changing the origin of the angular momentum, and this is what is happening, right? Angular momentum is defined up to some initial position, so if you act with a translation, you add a little bit of p mu to angular momentum, so everything is fine. I mean, the fact that these things transform into each other, they have a physical meaning, which is reasonable. Yeah, thanks for this question. Any other question on this or other things that we discussed before? Okay, so now next step is, this was just construct the BMS coordinate system, but of course the reason why it's useful was BMS realization that now you can solve Einstein's equation order by order. So I'm going to write it here. Theorem. This is the essence of BMS work from 1962. Is that once you've managed to put your metric in this form, so either it's some sort of nice guess that you have, or you like Penrose's definition and you derive it. So now assuming that, that assuming the expansion so we want to assume that each of the coefficients can be expanded in powers of r. Ya equals sum from I equals 0 to infinity of vi u of ya r to the minus I, etc., etc. Ua u r ya equals sum of I equals 0 infinity ui. So, etc. So you assume some sort of formal expansion like this, and you solve order Einstein's equation. This one?
Yes.
So again, you see, yeah, the leading term is going to be 0. Yeah, so the leading V0 will be 0, and then you have to solve the order by order. Yeah, maybe you could say I equal 1 or something. Anyway. Then one can solve, and here I'm going to solve pure, or I'm giving the result for pure Einstein's equation. So Einstein's vacuum equation, order by order. And find the following behavior. So the most important part is the metric itself. So H, it starts like the round metric. So this was this universal structure. At second order, you have something which is called the asymptotic shear. It depends on u, z bar. And then you have subleading coefficient r minus 2 that people write d ab plus r minus 3e ab, etc., etc. And what's going on is the following thing. Absolutely. Yeah. Well, nowadays everybody's used BMS coordinates, so we sort of, and everybody use C. So So this is the universal structure from yesterday, from yesterday. Universal structure. So this is the boundary metric. This object is a free function. So what's important here is that it's not constrained by Einstein's equation. And it's called the asymptotic shear. This is another way of thinking about the presence of gravitational radiation. Sometimes people, so I think Ashtekar or maybe even Gerard call it the radiative structure. Radiative structure. This is this object which encodes gravitational radiation. And so if you wonder, because I was talking about the psi4 just before, so the psi4 0 is du of CZZ. And then these objects, they must satisfy evolution equation of the form, let's say, du EAB equal something, etc. Well, du, I think du CAB is 0 anyway. This cannot depend on you, etc., etc. And here you have, this is typically a function of the shear. So the way you think of it is that these guys, they are the shear, which is the radiation going at cry, is fluxing these terms and fixing the way they evolve in time, in U time. But the initial value isn't fixed. So there is a zero function, zero mode initial time thing that you can choose. D, yeah, okay, thank you. Thank you. This is this D mode, which is 0. And then almost all the other coefficients are fixed by the Einstein's equation. But so beta is completely fixed, plus O of R minus 2. And this is like so the other field are other field. So there is nothing interesting in beta. In the V, you have the following thing happening is that it's minus R minus 2 over 2 plus R minus cube of 2m. And this U, Z, Z bar plus fixed term. So the subleading terms are completely fixed, but again here we have just evolution equation, dum equal, well, I'm going to write this, equal du CAB plus blah, blah, blah. So this is Bondi mass aspect, Bondi mass. And again, you should think of this mass. So if you were doing Schwarzschild, this would be your usual mass. But you should think of the mass being, of the energy of your spacetime being fluxed by this nu squared. So this is nu AB. This is just a definition. So flux of radiation. And UA will give you the angular momentum. R minus 2, 1 half D C A plus R minus N this function is the angular momentum aspect, and again, you have an evolution field equation on it, GU and A equal some flux term.
So this
Yeah.
volume should be okay.
Right. Yeah. Okay, so indeed, this was one of the, so unfortunately, my proof got slower than I thought, so I will not be able to say all I want, but yeah, so as Jerzy was pointing to, so what people call, so gravitational field, the invariant object is second derivative of the shear, but you can already think of this, you should think of the shear here as the free data in your evolution process. You're trying to solve a field equation, Einstein field equation. In doing so, well, you need to choose initial data. So usually what you do when you do your usual initial value problem is that you need initial time and speed to solve your second order field equation. Fine. But usually in Einstein field equation, you have constraints. For example, this would lead you to the Wheeler-DeWitt equation or etc. Usually you have constraint on your initial data. Here, however, we are solving Einstein's equation from Scry, which is a null hypersurface, which is completely changing the behavior because the surface is null. So it's completely changing the way the field equation organized. The mathematician called this a characteristic problem, solving a PDE from null surfaces. In this case, what BMS found out, which is a feature of this type of way of solving Einstein's equation, is that you have a free function. There are no constraints on this field. So this field here are the initial data for solving Einstein's equation, and there are no constraints there. It's a very striking feature of characteristic problem is that you do not have to solve the usual constraint associated with gauge invariance that you expect when you have initial value problem in GR. And this all has to do with characteristic problem. This shear also you should think of it as being identified with, indeed, was Sabrina presented in previous lectures. These are your infinitesimal gravitons at Scry. This, if you were to linearize the theory, one thing, a good exercise you should try to do, I mean, it's an immediate exercise. You take the BMS expansion, you linearize it in the shear. You just linearize. What you will find out is the same expression. You will find Minkowski together with the linearized term, which will be this shear. So this shear, you can think of it either as being a linearized gravitational field at Scry, or as being, and then this really is a gravitons, and you can run your free quantization theory on this, or as the free data for solving the full nonlinear Einstein's equation. So that's an essential feature of this characteristic problem. I think that's why we are here, I mean, deep inside. One of the reasons for which Scry is well adapted to quantum field theory is that it's really a situation where one field, you really cleanly see as a geometrical picture that one field, this shear, is at the very same time, once again, the linearized graviton of your free theory and the free data for the full nonlinear perturbation theory. So that's the that was the message. So how much do I don't have much time left? Okay, let me just write the relationship, the asymptotic.
Can I ask a question?
Please, yeah.
So besides the data in CAV, there's also initial conditions for all of these other equations. Right?
Yes.
Are we demanding some particular behavior in U? Otherwise, DAV is also some free function on the sphere.
Yes. Yeah. And also you have a free function for each of these tower fields. So for one thing, yeah.
Does this freedom of initial condition also is connected with this aspect of choosing initial conditions like quantum cosmology program? Because you mentioned Wheeler-DeWitt equations, right? And is there some prescription to fix this initial data, even if we were able to solve the wave function of the universe or whatever, we still have to fix the initial conditions somehow. Does this procedure something for us?
So for one thing, I think you should think of these things really as initial condition for a type of scattering problem. So trying to send gravitational waves inside your spacetime. The shear is really the amount of gravitational waves, but you also have a lot, maybe some picture would be more illuminating. So really, you're solving Einstein's equation for a null cone at scry. The shear is the free data that you choose here, but you also have this tower of fields that you need to choose here. So as I was mentioned, maybe EAB as at I minus, etc., G, etc., etc. So, or maybe you want to solve it from I0, depends on what you want to do. So, I think it really depends the type of physics that you want to solve. If you want to solve a scattering problem, it seems that the most obvious thing is to take everything to 0. Just really start from Minkowski, send a gravitational radiation, and try to figure out what will come through. One thing you would know is that these guys will not be 0 at, will not then be 0 at space like infinity, and also should not be 0 in principle at I+. You will have to sort of work hard to whether or not. And this is one way of thinking of the memory effect and all these things is that you have these fluxes and you have no idea. I mean, there's some sort of conservation rules should tell you what the value of this value at I+. So otherwise, you could, choosing these things is really about the type of physics that you want to describe and that you're trying to model with this spacetime. Some remark about this in terms of counting the degrees of freedom. It should not be a surprise that we have an infinite tower of fields here. Because if you're trying, again, from the perspective of solving PDEs, if you're trying to solve Einstein's equation for an initial slice, a time like, well, you know that you expect 2 functions of 3 variables. Okay? Now we are solving the problem at scry, but the numbers of 3 functions to be the same. We have 1 function of 3 variables. That's good. We need another one. But in fact, it's there. It's just packaged in a very strange way. It's just you're packaging a function of 3 variables as a formal series of function of 2 variables. So the counts seems the same. It's just organized in a completely different way because it's a null problem. It's a characteristic problem and not your usual timeline characteristic problem. Okay, so I'm not going to have, so what I wanted to conclude on going back to asymptotic symmetries, one thing which I'm sure you will see other people discussing this, so I'm not too afraid that I don't have time to discuss, is that you can take this metric, look for fields, linear vector fields which preserve the form of this metric. So, and this would be asymptotic symmetries, and you will find out that you'll recover the BMS group that I discussed yesterday. It should not come from the way I presented everything. It should not come too much as a surprise, because you see that this BMS coordinate system is completely controlled by the data at scry. So really, this coordinate system is produced from the coordinate system at scry. We saw yesterday that the BMS group acts at scry, so it should not come as a surprise that it's going to act there and be in asymptotic symmetries. Okay, this is the message I wanted to convey today. Okay, so yeah, maybe thank you and then yeah.
Mm-hmm. And I know the derivation from the killing fields of this metric, where you would say, okay, so you have some complex killing vector field at the end, and if you take the real part of it, you will get the normal BMS group, and if you take the whole part, you will get the, like an extended algebra, which would also be super. Or like, I don't know, like, can you comment on how these killing vector fields that you get for this metric are connected to the topology and to this extent?
Okay, so. You see, in all that I discussed today, I'm really nowhere using the topology. This is just about local coordinates. It's just little games about, I mean, you're just working in some local patch at scry, constructing a local coordinate system along scry, and I'm not even saying what these Z are doing, whether they form a sphere, maybe they form a torus or anything, maybe they are just the plane. None of what I discussed has to do with that. So the naive computation will just give you that, again, the BMS group is the group of conformal vectors on the plane, which is this huge Euler-Zero group. Well, I'll do it. And so once again, what takes you from your infinite dimensional group to the Lorentz group is just the topology of Scry. So, yeah, I don't know if this is answering your question. I mean, it's very...
So you basically say, like, the kilometer fields that you get for that
will be...
shows if you go, like, for local conformations,
Yeah.
so global ones.
Do the naive calculation here, you would just get your infinite dimensional holomorphic functions, because all of this does not know anything about the topology at this stage. So it's really for you to add, to say, oh, actually, I want the z coordinates to be coordinates on a sphere, so I want specific behavior as I go to z goes to infinity. This will fix, this will be a very strong requirement, take you back to Lorentz group. But, yeah. Another question? Yeah, so, if not, thanks a lot for attending the lecture.